my name is Ryan Morlock.
And my name is Lenny Pope.
And our machine learning project will look to estimate the bandgap energies of inorganic crystalline solids from tabulated material state. The Materials Project is a database that stores experimentally measured and computationally derived material properties. It contains information on over 130,000 inorganic compounds. Our model will train on inorganic compound entries in this database to estimate material bandgap energies. The bandgap is an important parameter in identifying prospective compounds for a number of engineering uses, including the semiconductors used in solar cells. Some features we believe to be important in bandgap predictions include the type and number of elements in the compound and the material's crystalline geometry and stability. Other features we believe to be important, such as the density of states shown by this graph, are tabulated by the Materials Project but are difficult to enumerate for a machine-learned model. As depicted, the database requires a minimum of 8 features for an entry to be accepted. These include the chemical formula, formation energy, bandgap, volume, and density, among others. Depending upon the entry, other properties, including the lattice parameters and decomposition compound, might also be reported. We intend to screen and re-engineer these features so that the optimal combination is used as predictors for our model.
Our general approach to this problem space is to 1. Pull down a usable subset of material properties from the Materials Project database, 2. Remove unusable edge cases in our dataset, such as zero placeholder items, 3. Engineer features based on physical and chemical knowledge of materials, and 4. Apply a machine learning method to our dataset. Describing chemical formulas as a numerical value is not a straightforward process. Using each row and column number as a feature breaks down when more than one chemical is being considered. For this reason, we decided to create one-hot features for each column and row of the periodic table to maintain chemical identity. This avoids mixing of chemical identities into a continuous scale while only creating 25 one-hot features, as opposed to creating a one-hot feature for each element. For features that do act on somewhat of a continuous scale, we can use stoichiometric averaging, where we estimate the material properties of a compound as the stoichiometric average of the pure component properties, following the formula below. As we are looking to predict bandgap energies, a continuous variable, the algorithm of choice is a form of regression. We plan to implement linear regression, ridge and lasso regression, and support vector regression to determine which method works best for our dataset. In particular, we believe the problem to be highly nonlinear, so we expect support vector regression to be the regression of choice, as it can be used to generate higher dimensional spaces to tackle these nonlinearities.
That's the end of our presentation. If you have any questions, please ask them now.